Okay, so let us get started. So it's a pleasure to have Gady Kozma here for the third talk. In terms of the next schedule, so next week we have 3 lectures by Nina Gantert, followed on Friday by 2 related research talks, 2 short research talks. So the schedule is on the website. As before, this lecture is being recorded, so if you do not wish to appear in the recording, then please turn off your video and mute your microphone. A reminder that it is nice for other people to see your real name in the chat window and in discussions, so please use that. We will be about 1 hour of the lecture with a short break in the middle for questions and to take a breath, and there will be further discussion afterwards, and if people stick around and are interested, also breakout rooms. So with that, it's a pleasure to have the third talk by Gady Kozma. And Gady, will you share your screen and we will get started.
Okay, everyone can hear me fine?
Yes?
Yes,
Can
yes.
people hear me? Okay,
Yes.
good. Okay, so welcome everybody. Thanks for staying for the last and I'm afraid most demanding talk of this mini course. First talk was about things that were known since the 80s. The second talk was about these results from 2015. And the last talk, which will be about results which are not yet published, of Hugo van San and myself. It's just a lemma. It's not a very important result, but it's an interesting application of this theorem of Cerf, and therefore it somehow I hope it will demonstrate why I believe that this is an important theorem and a breakthrough in understanding of critical percolation. But again, there are no references, so the only reference is actually the slides which are on the site. So try to hang on and don't hesitate to ask questions, because there is no more detailed versions where you can get the details. Okay, so let's start. So this is where we left off last time. We stated this theorem of Cerf. Let me remind you the notation again. Lambda is a box, so lambda n is a box from minus n to n in all dimensions. We are in, say, in dimension 3 or in arbitrary dimension bigger than 1. And this is a smaller box, but not that small. It's n to some constant. The value of the constant would not interest us. Or it interests, but not the precision of, of the numbers here. And this notation, which is the most, which is not standard notation, but it's especially for this talk, means that there are 2 clusters from the smaller box to the boundary of the bigger box, which are clusters in the bigger box and disjoint different clusters in the bigger box. And as people already asked in the first time, they are allowed to extend outside the box and intersect there, but not inside the box. And the theorem says that this probability is decaying in n in a polynomial rate. Okay, so in order to not carry around this 1 over a, let's eta be some number smaller than this. So I won't have to carry this number around. Okay, I'm going to start with a lemma which looks a bit strange, but I will need it, so But this is really a lemma, so I'm not going to motivate it beyond how it appears in the proof of later, but it demonstrates an interesting and important principle, which I think that people who are not experts in percolation should certainly be aware of. So let's see what the lemma states. So you look at cubes of side length n to eta. Remember, eta was from just some numbers smaller than this in gamma n. Okay, so I don't mean all cubes. Let's just imagine that this divides n. These kind of divisions are not important, and just take a collection of points which form like a lattice, which are disjoint and touch each other. Okay, so I'm interested in these boxes which are basically form like a renormalized lattice inside the gamma n of n to some small power. And I'm bothered with clusters which touch too many boxes. So the number of boxes is n2 d times 1 minus eta, and if a cluster intersects 7/8, the exact number is not so important, but this lemma can be proved with any positive constant, but I do 7/8 for just to be explicit. Then the probability, then that cannot exist with the probability that this cannot be too large. It's bounded by some constant which depends only on the dimension. Okay, so think 0.99. It might be 0.9, but it cannot be 0.99999. It cannot go to 1 as n goes to infinity. And again, I repeat that this is definitely a critical phenomena. I mean, at P bigger than PC, such as large clusters exist with probability very close to 1. Okay, so let's just repeat. So again, the probability of a cluster which intersects too many sub-boxes is not too close to 1. And no, it's all the boxes. Look. Yes, I see this question. Yes, I have the chat open. So, I'm looking at all. Take the cube. It's a pity I can't draw. I'm missing a board. Take the cube, the larger cube, which has size length side n, and divide it into n. Maybe this number is written somewhere. No, unfortunately, divide it into n to power d times 1 minus eta smaller boxes. Okay, and I'm large if intersects a majority, a 7/8 of the boxes of all translates of the box of size n eta by numbers which are multiples of n eta. Okay, so let's see how this is. Okay, so let's note this event by E. This is just notation, and let's assume that E happened for 2 boxes. Look at this number, n½ So I'm looking at the box lambda n. I'm translating it by half. So the new box, the translated box, somehow overlaps the existing box by half. And I'm asking that, and I'm denoting by E prime the event that the translated box also satisfies the same property. So let's understand what do I mean here. So there is a cluster in the original box, okay, which intersects 7/8 of the smaller boxes. And E prime is that there is a cluster in the translated box which intersects some boxes of a big proportion of the smaller boxes of lambda prime, but it doesn't have to be the same cluster a priori. We will soon see that it does, but it doesn't have to be. Okay, so let's see. So let's assume that both E and E prime occurred. What does it mean? There is one cluster which intersects everything but 1/8 of the cubes of gamma n, and another cluster, or possibly another, which intersects all but 1/8. So if you add those descending cubes, you get no more than 1/4. So there are at least 1/4 cubes that intersect both. Okay, right? Because the intersection of gamma and gamma prime is only half, contains only half of the boxes, and there is a quarter that we threw out because which came from 2/8. So the conclusion is that at least a quarter of the cubes in the intersection, look at this quantity. This intersection is like a half cube, right? Because we have a cube and a cube translated by n half, so the intersection is a half cube, contains half of the small cubes, and a quarter of the small cubes in the intersection intersect both C and C prime. I really should have drawn a picture here, sorry about that. So what happens if these clusters are not the same? Here, this is the point. This means that each of these cubes satisfies the two disjoint clusters event. This is the point, because they have, each of these small cubes has the cluster C coming to them. Each of these small cubes have the cluster C prime coming to them. If the clusters are disjoint, then this means that they have two disjoint clusters going quite far. And we know that by Cerf's theorem that the probability for that is small. If we use also Markov's inequality, we see that the probability that there are many of them is quite small. So let's understand exactly what is written here. The probability that E happens, that is, such a large cluster exists. E prime happen, such a large cluster exists in the translation, and they are different, is smaller than n2 minus f4, because it implies too many boxes where Cerf's theorem does not hold. Questions about this inequality? This is the crucial inequality. If you understand that, the rest of the proof is a pretty standard.
So there is one question in the chat from Jens.
No, the union is an arbitrary union of boxes. I'm not interested in the shape of the union. Okay, we have many small, I'm just interested in their number, right? There is some, we know that for every cube, small cube, the probability of two disjoint clusters is small. So the expected number is smaller than n times minus 4 times the number. So by Markov's inequality, the probability that there are many of them is small. But I'm not interested in the shape of the union. This is okay. So let's okay. The slide will now disappear, except for this formula. Oh, okay. No, I'm sorry. It was just compacted. Okay. So we have most of the text of the previous, and the Cerf's theorem disappeared because we already used it, and we have this crucial formula here where you can still read it. Okay. But this means that what? Let's see. That the probability, if the probability, there is one difference from the previous slide. I gave this C a number. I replaced C with C1 because I want to use it. So what is the probability that these clusters are equal? Well, we have the probability of E, which is 1 minus C1, and the probability of E prime, which is also 1 minus C1. So if we assume the opposite, then the probability that both E and E prime happens is at least 1 minus 2 C1. And we have this bad event, which we also subtract. So with this probability, these big clusters are one and the same. Okay, this is just a reformulation. Now here is our favorite, remember, how do we prove things about PC? we change P a little and get a contradiction. So this property, okay, sorry, I won't try to select things. This inequality is an inequality which holds in a restricted volume. It holds in a box of size, okay, n times n times n times 3/2 n. Okay, it's some property of finite space. So if we take P slightly smaller, can depend on n, that we are proving this lemma. So I'm assuming by contradiction that this is bigger than 1 minus C1. So if this holds, so our contradictory assumption implies that this inequality holds. By continuity, if we take a slightly smaller p, certainly this smaller p can depend on n, no problem. This will also hold, maybe with a slightly bigger constant. And here is the crucial point. There is a theorem of Liggett, Schonman, and Stacy that says that if this number is too big, then you will have an infinite class. This is an extremely useful trick in percolation. And if people understand that, they certainly learn something. So let's understand, maybe I will show the statement of this theorem of Liggett, Schonman, and Stacy. Okay, so here is a statement. For every d is the dimension as usual, and k, there exists some epsilon, such that if you have any dependent percolation, so some bits which could be dependent, but A, they all happen with big probability, and they are independent if you look at distance larger than k, then you have an infinite cluster with probability 1. What will our bits be? Our bits, okay, now let's close and I'll show it again if it's necessary. So let's understand how this theorem of Liggett, Schonman, and Stacy helps us. I'm claiming that if this probability is big, then the theorem of Liggett, Schonman, and Stacy, because this probability, if you look at the boxes which are, now I'm dividing the whole space into boxes of size n, not of size n to the lambda, of size n, okay? And I've shown you that with probability quite large, in two boxes, let me take questions after I finish the explanation. So I'm dividing the whole space into boxes of size n, and I want to construct an infinite cluster. I want to jump really from box to box while keeping the connectedness. What allows me to keep the connectedness? This fact, which is written here. So what I'm saying here, I'm starting with after our first n. When I move neighbor, I know by this line here that with quite large probability, there will be a big cluster in that neighbor, which is the same. When I move to a big probability, this cluster will be the same. So if I find an infinite paths of such n boxes, such that all the clusters are the same, then I will construct an infinite cluster. And the theorem of Liggett, Schonman, and Stacy tells me that it's enough that this probability be bigger than some constant smaller than 1, 0.99, say, for this to happen. Okay. So again, what is the contradiction? We assume that we took p slightly smaller, found an infinite cluster. So it's a contradiction because we know that for any p smaller than pc, all clusters are finite. Okay, so this is the proof of the lemma. So let me now just see if there are any question. So I see that there's a question, why is the continuity in P? Okay, this is certainly something, let's explain that. That's easy to explain. This event is an event that depends on only finitely many edges, because it's all contained in two boxes of size n, which are neighbors, which are like, one is translation by n half of the other. Here, this n half is still written. Okay, so it's an event that depends only on finitely many edges. Events like that, the probability is a polynomial in P. And this is something completely generic. So if you have an event that it depends on, I don't know, 10 edges, then the probability as a function of P is a polynomial of degree 10 in P. Or it could be, the degree could be smaller. Okay? So this is the continuity that is explained, that is written here. It's continuous because this event, this argument is somewhat delicate and an extremely useful trick to realize. We do the reduction on P for an event which is local. Even though this event is local, it implies the existence of an infinite cluster. It's quite confusing. So we find something, some local property, which implies an infinite cluster. And this immediately leads to a contradiction in PC, because in PC such an object cannot exist because of this argument that is written here. You can reduce P because of continuity and then get an infinite cluster where you shouldn't get one. Okay, I see that it was already answered in the chat, but still, I think this point was sufficiently important to actually answer it even in the talk. Okay, so the constant, I see another question. Why doesn't the constant depend on n? Because the constant in Liggett, Shulman, and Stacy doesn't depend on n. It just, okay, let's move on and maybe take more questions. Okay, and to use this lemma, okay, let's skip that. We don't have so much time. This was, we skipped the technical point. Let's not bother about that. Okay, so here's what I want the lemma for. Okay, so let's see what this. Now that I've stated it, you will feel a little bit why we never published this, because this result is really a little bit disappointing. Let's see what the result says. Suppose for any d, okay, we will actually use a d is bigger than 3. It's not a big deal, but we will actually use that. You will see how. So if d is bigger than 3, there exists some number, okay, such that the probability that the box of size, again, a small mesoscopic box of size n to some small power, is not connected, is bigger than some constant n to minus d. So look how disappointing this result is. We actually think that this probability is going to 1 as n goes to infinity, for nu sufficiently small, not for any nu. But for nu sufficiently small, we certainly think that this probability is going to 1, because we are at PC by the standard conjecture, connection probability decays polynomially. So what happened here? Okay, so by the standard conjectures on critical percolation, if you take, you don't have large, smaller boxes should not be connected too far away. There are even quantitative estimates or conjectured estimates. So this probability for nu sufficiently small and n going to infinity should go to 1. It should be typical. This non-connectedness event should be typical. And the only thing we can prove is that the probability doesn't decay exponentially. Okay, so is bounded below by some polynomial, by a polynomial. So this is why we never published it. And I am not claiming that this is an important, yeah, this is a dimension always. I'm not claiming that this result is so important. I'm just saying that it's a nice application of Cerf's theorem. We've already seen one application of Cerf's theorem in the lemma, and there will be another application of Cerf's theorem in the theorem itself. So let's go to the proof. Okay, so assume by contradiction that this probability is in fact, okay, so the probability of the complement, the probability that the box is connected is bigger than 1 minus n2 minus t. What does it mean? It means that with very large probability, all the boxes are connected. So again, when I'm saying each here, okay, or all, when I say each box, I mean, again, like we did in the lemma, I'm taking boxes of size n to the nu. I'm taking a lattice of them so that they are touching but disjoint. And so there are something like n to power 1 minus nu times d such boxes. And just by because we know that the probability of connection is so close to 1, then, or the probability of disconnection is so small, then even if you sum them over all boxes, it's still small. So we will have that all the boxes are connected to the boundary. Now, this doesn't say anything about clusters. They could be connected with one cluster or with many clusters, or maybe one large clusters and maybe many small clusters. All we say is that all the boxes are connected. Okay. So let's denote this event by A. And okay, there is some issue here with, yeah, in particular, it means that this fact, because if our smaller boxes, our boxes of size n to the nu are inside n to the fourth and connected to a shifted box, and it will also, okay, this is not important, all this playing around with clusters, with fractions, okay. Okay, so this is just, it's a stress because it's a notation, it's a convention that will be used throughout the proof, but it's not so important. So all the clusters are clusters that go from the fourth to n fourth to n half. Okay, so the whole of the previous slide is now summed up in this little claim. Our event A, which I remind you has very large probability very close to 1, implies that all the boxes are connected. So I'm taking a union boundary. All the boxes are connected, and this happens with big probability. Okay. So maybe it's not a good time for a break yet. Okay, so let's continue a little bit more before having a break. Now for any cluster, what this proof is about understanding how many boxes various clusters have. We know that all the boxes belong to some clusters, but we don't know how many clusters there are and what's the distribution of the sizes. We are working here with some partial knowledge, and we somehow have to accommodate that. So for every cluster, let n be the number of n to lambda subboxes, again, of this, probably it should be quarter, that intersect the cluster. Maybe it should be half as written. Okay, so as under A, we have that, in fact, this sum is at least n to d to 1 minus nu, because we know that all the boxes belong to some cluster. So, and of course, one box might belong to more than one cluster. There could be many clusters that get to a box. That's not a problem. So this is certainly an inequality, not an equality. Okay, so let's understand again. We sum over all clusters which go from n quarter to n half. For each one, we count how many small boxes it reaches. And this sum should be at least the volume because of our assumption, because we are working under this variable, under this event that states that all the boxes belong to at least one such clusters. Now we use concavity. Look that there is a word here that appeared. Now we use concavity. Concavity of this function, x to power d minus 1 over d, tells us that this is smaller than this. If you don't know this fact, prove it as an exercise, it's simple. Okay, and now we are going to use the lemma. It's a bit tricky, so be careful. Not really tricky, okay. What is the difference? The difference is only that I'm added the condition that the cluster is small, okay? Here I summed over all clusters, and here I want to sum only on small cluster. Where small is of course the opposite of large. No, this is written. This is written correctly. Check this. The number of clusters doesn't appear. It's not. Okay, sorry. So small here is the opposite of large. So let's understand just this inequality and then take a break. Russ saves me. So this inequality is called Bernoulli Inequality. Okay, good. Thanks, Russ. That was helpful. Okay, so why am I allowed to write this inequality? Okay, let's see. We know that under A, and A, remember, I remind you for yet another time, happens with probability going to 1. It happens with probability very close to 1. And in this case, this sum is bigger than, okay, you have to replace here d with d minus 1. But we know that with probability at least 0.99, there is no large cluster. So with probability at least 0.01, there is no large cluster. So there is a part which has a probability at least 0.01 where both things holds. You don't have large cluster, and this sum is bigger than this. And therefore, you get an estimate for the expectation. So I hope I explained this. Let's take a 5 minutes break, and then I will take questions up to this point. Okay, so 5 minutes break. Okay, let's see what's going on. We didn't use d bigger than 2 yet. We will, but we haven't used it yet. I certainly didn't explain yet why do I choose here d minus 1 over d. All this will become clear.
So why do you need also this 0.1 event that there is no large cluster for this inequality?
No, so I will need it later.
You just say,
okay. I will need it later when I use the isoperimetric inequality. All this will become later. We are still, it's not, maybe it wasn't the best point for a proof because everything is still quite mysterious. Maybe it wasn't the best time for break because everything is still quite mysterious. It's not clear why I want here small clusters. It's not clear why I'm interested in this number. Maybe it was, okay, I hope it will be clearer later.
And just to be sure, so this is all under the assumption that the event in the theorem with Hugo and Vincent has a high probability.
This is all under the contradictory event that actually, no, this is under the contradictory event that it has probability small, that the non-connectedness event has probability small. So small that in fact all boxes are connected.
That's right.
Okay, let's continue. I think the 5 minutes are more or less past. Okay, so I guess there were not so many questions in the chat. So I guess so far, at least the argument is clear, even if the motivation is still in the dark. Okay, so let's go. Okay, so we won't be using this lemma about large clusters, so I hid it. And but here is the last thing that we concluded, that this expectation is large. Now to continue, let's remember this argument of Gandolfi-Grimet.
Sorry, there is one more question just in the chat about the union bound.
And
If there should be a
there
factor of
factor
n to the d minus nu.
Yes. And there should be, Leo is asking if I didn't make a calculation mistake when I did the union bound. No, the probabilities are n2 minus d, and I'm summing over n to d times 1 of minus n, and there are n to the power, open parenthesis, d times 1 minus nu, close parenthesis, boxes. So there is, so after the summing, I still have left over n2 minus d nu. Okay, so but let's go back to this Gandolfi-Grimet-Rousseau argument that we covered the last hour. What did it tell us? It told us that the probability that you have two disjoint clusters going to distance n to the quarter is, I want to focus your attention for yet another time. We already discussed very shortly that the crucial quantity that you get there is the sum of the square root of the sizes of the clusters. Okay, I'm not going to use the result, but the eventual result, but I'm going to use this intermediate claim that it's the sum of the square root of the sizes of the cluster that really calls the shots. Okay, I hope you remember that. Now, okay, here there is again more technicalities with n quarter and n half. Trust me that it's okay. This part is written a bit more detailed than a normal presentation would be written, simply because it's the first time that I've written this proof. so it's also a bit of a paper. But so there are some businesses here with n over quarter and n over half that we don't want to know about, and I'm going to skip. Now, again, this is a part of the argument which unfortunately I didn't have time to show yesterday, and I also don't have time to show it today. But so you will have to trust me here. But the part of the argument that is in Cerf's paper, so you could read it there if you needed to, that says that from the probability that okay, this should be two neighboring points, I'm sorry, and also here. From the probability that two neighboring points have two disjoint clusters going to distance n to the quarter, you can get to the probability that a small box has two disjoint clusters going to distance n quarter, and pay n to some power of the size of the box. This is the same argument which I didn't show in Cerf's theorem last hour. I'm going to use it again. It just says that there is a connection between these two probabilities, which again is some kind of patching argument. Now, let's put this estimate here. So you see, I just put it here. There is no problem. There's nothing interesting in this line. So you get n2 minus d half plus some constant. These terms are not important. Don't bother about them. This is the important term. You get n2 minus d plus something which can be made small if nu is taken small enough, times the sum of the square root of the cluster. So I just copied. Okay, I'm doing this calculation in details because this is the core of the argument. Okay, but still it's just a calculation. let's go. So this is just the conclusion of the previous transparency. Okay, it's written exactly. You see the same n minus d half plus constant nu, and the same n minus d plus constant nu, and the same crucial sum over square roots of the clusters. And here's the second point of the argument. Let's remember what is the isoperimetric inequality. Okay, what is the isoperimetric inequality? It says that any set has boundary at least the size of the set times to power d minus 1 over d. Okay? Now, we are going to use the isoperimetric inequality after restricting to boxes. So it's a boxed version, but it's the same inequality. And what it shows that if you have a cluster, then there should be many. Remember what this notation, this notation is still around. It's the number of n new sub-boxes that intersect this cluster. There should be this number of boxes which intersect the clusters but have a neighboring box that does not intersect the cluster. Okay? And this is some kind of local isoperimetric inequality. And here it's very important that the cluster be small. I remind you the definition of small. Small means that the cluster does not reach more than 7 over 8 or some constant, it's not important, of the boxes. There are still many boxes which the cluster doesn't reach. So the point is, so this is here is very important, because if the cluster reaches all boxes, then this set would be empty. And so this is clearly false. Okay? So it's important that the cluster is not large. And then we know that there will be many boxes which intersect the clusters but have a neighboring box that does not intersect it. We're almost there. Hang on for a few more minutes. Let Q be such a box. Again, we are talking about an n to the new sub-box. And let Q prime be its neighbor that does not intersect. Remember that our event A, that all the boxes are connected. This implies that the union of these two boxes is connected to distance n quarter by two disjoint clusters, right? Because all boxes are connected, and we know that Q is connected to C, and Q prime, that C reaches Q but not Q prime, and Q prime has some, therefore, whatever the cluster that reaches Q prime, it must be different than C, and we get our two disjoint clusters. Therefore, you have this many boxes of size 2 nu and nu, which are connected by two disjoint clusters. Okay? I am taking the sum over all small clusters, and for each one I'm looking at this boundary, this number of boxes which have this neighboring box, which are this property, and I can just sum them. Okay, so here it is written again. Okay, now there is some overcounting in this argument. When I summed over the clusters, there was a little bit of overcounting because one box may appear in various places, but this overcounting is no more than n to the nu, which I don't care about. So what did we get? We get that the number of what does it mean such boxes? It should be written here. Okay, here it is. Boxes of size 2n nu, which are connected to distance n quarter by two disjoint clusters. So this number is bigger than some factor that comes from overcounting times this sum that we explained came from the isoperimetric inequality. And this is it. We take expectations, and we get essentially a contradiction. So let's understand this. The difference between here and here is just taking a expectation. This was under A, and this is exactly the same thing, but I took expectation and used the fact that A has probability going to 1. So the expectation of this would still be larger than the expectation of this. You see, it's just copied. And this last inequality, I took this guy and put instead our estimate from a few transparencies back, which is still written here, basically by the Eisenman-Keston-Newman Cerf argument. So I get, so you see, it's just a formal, I took what is written here and copied it. And this is then, let's see what we got. Okay, we still have to bother with this smallness, but this is not a problem. We can discuss this later. And let's see what we got eventually. We got something that cannot be. We got that the sum of the square roots, it should be bigger or equal. Here it should be bigger or equal, is bigger than the sum of the powers d minus 1 over d. There is some factor here, but it doesn't break the argument. So why doesn't it break the argument? Because everything is multiplied by nu. Okay, so let's and if nu is sufficiently small, this is a contradiction. Okay, so maybe I will just show you the proof in a nutshell, and then actually I don't have much time, and I didn't plan to show anything else. So let's understand the proof, the overall structure of the proof. Okay, on the one hand, we got that from the Eisenman-Keston-Newman argument, we got that the probability that n to the nu is connected, that the box of size n to the nu is connected to lambda n is smaller than some sum of all clusters of the square root of the sizes. On the other hand, our contradictory assumption, the isoperimetric inequality, and the fact that there are no large clusters, we used all three, gave a bound which had powers d minus 1 over d of the same quantity. Okay, so so let's remember again, why did we use all three? The contradictory assumption that this probability is very small meant that all boxes are connected, which allowed me to use the isoperimetric inequality, because which meant that the sum of the boundaries covers everything, that the clusters cover everything, so it gave me some bound on the clusters, and I needed the fact that there are no large clusters to use the isoperimetric inequality. Because if there are no large clusters, then I can use the isoperimetric inequality for each cluster. And these two things contradict. So I don't have much time left, and anyway, I don't have too many things to say. So please feel free to ask any questions about the proof, because I'm basically done. Okay, I see that there was a question at some point in the chat, where did I use d bigger than 2? Now you can see why I need that d at least 3, because at d equal to 2, this is square root, and there is no contradiction. Contradictions comes because in 3D, the boundary is bigger than square root of the volume. Of course, the result holds also in 2D, but using a different argument. Okay. Any other questions about this proof? And Omer at some point asked, why do I need this fact about small clusters? I hope this became clear, to use the isoperimetric inequality. Okay, so if there are no questions, let me make just a few remarks and we'll finish. First of all, if you go through the calculation, you can get an explicit number, for example, 1/60. Okay, certainly, like everything else, improving it should be useful, but I can't, give any particular reason or magical value where it's at this point it must be true. By the way, nu cannot be improved beyond half at no, so maybe even 1/2D in high dimensions. So it's not too, people who think too much about 2 dimension might think that nu should be improvable up to 1. This is not true. Okay, I should have written it, but I didn't. Okay, and let's finish with dependencies diagram for this entire mini course. Tells us, just ignore these two, which we didn't have time for, but we did have time for slightly sketchy proof of all these 6. So we actually did cover quite a lot of ground. So let's remember what we had. We had that we started with the fact that the expectation at criticality is infinite. We got from that the sum of the probabilities of connection to the boundary of a box is at least 1. From that, we got Cerf's lemma, which says that if you have 2 points in a box of size n, then they are connected in a slightly bigger box with a probability which is not too small. From that, we got Cerf's theorem. It says that the probability of, and of course here came the argument of Eisenman, Kesten, and Newman, that the probability that if you have that the probability of 2 disjoint clusters from a small box to the boundary of a larger box is quite small. From this, we got the lemma that we saw today, that the probability of a large cluster is bounded away from 1. And both things together, because we used Cerf's argument here during the proof of that, gave us our final result of like the final result of this course. And I've highlighted two of the claims in a bolder frame. These are the places where we used criticality explicitly rather than implicitly. These are all conclusions. So certainly if you use criticality in one, then it will fall, then you will need it in everything that follows. But here and here, we use criticality explicitly. Here, this, I remind you, this is the expected size of the cluster. How did we use criticality? We, again, assumed the contradiction that the expectation is finite, increased P slightly, and saw that even after increasing, there is still no infinite cluster, which contradicts that you are at least at PC. Yes. This is sorry. This should be smaller than. Sorry. Thanks, Gabo. And here we use the criticality explicitly by, again, assuming the contradictory assumption, assuming the opposite, assuming that this is bigger than 0.999, reducing P slightly, and constructing an infinite cluster. So you see how, okay, you can think about it as the same trick or not, I don't know, but it demonstrates the basically two kind of dual or similar, if you like, ways to use criticality to learn something. Okay. That's it.
Okay, so I will unmute everyone to thank Gady.